Charging by induction. This is the method that I call here, kitty, 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 kitty. This is a luring when you induce somebody. So think of gravity. You don't have to touch Earth to have gravity. No one needs to grab you and rub you on the Earth before you stick to it. The Earth reaches out and pulls you towards it from a distance because of this force field. Magnets do the same thing. When you reach out with a magnet, it can cross space and grab a hold. Charges can do the same thing. Okay? So, this works by creating the same situation in the thing that's approaching it. An object at a distance from a magnet is neutral, but clusters of atoms called magnetic domains, which are very fascinating. Every object in the world behaves like it's a bazillion magnets all randomly oriented. But as the object approaches the magnet, the north poles move towards this side because they're attracted to the south. The south poles back away. So the weird part is, as an object just approaches a magnet, it becomes magnetic too, but reversed. So these are attracted to each other. Now, wouldn't this mean if this is attracting that this south and that south should be pushing? Yes, they are. And this north over here is pushing there. Remember, I did a little bit on the inverse square law? If this south pole is twice as far away from that south, then its effect is 4 times weaker. As far as this south pole magnet occurs, in terms of the size of these magnetic charges that are in there, this distance from here to there is infinity. That's like saying you don't want to sit closer to a kid in the class you like because there's a kid you hate in Kentucky and you'll get closer to them as well. No, the distance is killing it. So this object becomes magnetic even before it's touched it. Here's an example of how this works. When you touch a paperclip to a magnet, this side of the paperclip is north, this side is south. So it's now a magnet itself, and it attracts another one, and the north and south poles are flipped. Okay? If you put a plastic paperclip in the middle, it wouldn't work. So we've got this induced magnetism. You've seen it every time an object heads towards a magnet. Now, for induction, what I want you to do here is make object A strongly net positive. If you think you can do this by watching my solutions, then you can learn to be a good musician by watching someone play guitar. Carry out what I just said. Make this object strongly net positive. Make this one completely neutral. Now, using the idea that I presented here, do the same thing. If object A approaches B, which charges in B would be attracted forward to meet the ones in A, and which ones in B would move away from the ones in A? So to make A strongly net positive, your best bet is to make them all positive for this case. So once you're done, what is the correct answer for B? Is B going to look like this one, or that one? Make sure you know how to do this. Now, here's a nifty thing we can do. We can trap these induced charges. So here's what you have to do. In position 1, create a charged object. Don't bother doing it as a complete charge. Just show a net charge. So make it all positive or all negative. Make the one on the right neutral. So show an equal number of positive and negatives. Now, on part 2, I want you to show the induced reaction. What will the charges look like on the second object here when this one's brought nearby? Now, the charges that hate what's approaching them will move away. where do you think they'll go when there's an obvious escape route? So I want you to show what you think will happen to these charges when they can actually escape this object. And at this point, I want you to sever the ground wire. Okay, so these two will be the same, except who got trapped in the ground? Now, when you move this away again, can this object go back neutral, or will it now have a trapped net charge? See me if you can't do this. Right? You've got to be able to think about this. And if you can't do it, you come see me. You're not getting a chance to just watch the solution. If you touch these two objects together, what will they look like after they touch? They will do their level best to neutralize. So give this one a try. These two objects, one of them is net positive, one of them is net negative. Demonstrate which way electrons would flow when you ground them to the water faucet. Should charges be going out or up, using the truth of the fact that only the negatives can move? If an object is charged enough, the negatives will leap through the air to leave or enter the charged object and render it neutral. They must reach sufficient voltage to break the gap, or they won't move. If you look at this, are the electrons moving down or up? Once again, think of water. If this was a spray of water, is this spray originating above or below? And this can give you a strong hint as to which way the electrons are moving, and then whether it's the cloud is negative or the ground is negative here. The sparking can only occur when the insulator that's blocking the electrons breaks down. So we've already discussed in the Van de Graaff the length of the bolt is related to the voltage. For example, air might need a spark of 200 volts to travel 1 centimeter. Could be 3,000 actually. But in this example, air's insulating capacity would be 200 volts per centimeter. So a 4 centimeter long spark would be 800 volts. This means that if you see a spark, you can see the direction of the electron flow from the shape of the arc, and you know its voltage by the distance it travels if you know the conditions of the substance. Additionally, the brightness, noise, and frequency of the spark can give you an idea of the current behind it. Obviously, if I said you pick one of these bolts to be hit with, you would know which one you would not want to be touched with. So the voltage is related to the vertical distance the bolt could jump, and the current is, think of these as rivers. Which one of these has a massive flow of electrons? In this case, where did the electrons originate? So in this case, the lightning bolt started on the ground. Now, which lightning would kill you more? Lightning that started from your head and spread out to the sky, or lightning that started to the sky and spread out and hit you? So oddly enough, the biggest fatality rate, is it you being hit by lightning or you hitting something else by lightning? And so again, here's my little example. Which guy would you rather be? The guy on the left or the guy on the right? Mommy, 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 my head's on fire. Did you go ahead and pick on that cloud again today and strike it with lightning? Well, it serves you right. It's kind of like punching someone and breaking your own hand. And the next part we're going to look at, is I'm going to pause it here because I know I'll run out of time, is why this works. Okay. Oh, wait a minute. What the heck? Let's do it anyway. This one here, if you draw this as a neutral object, and this one is charged, Can you explain?